In the previous lecture, we have discussed Rowe-Blackwell theorem as a second method for finding minimum variance unbiased estimators. We are going to start our lecture by illustrating Rowe-Blackwell theorem through an example. Remember that in Rowe-Blackwell theorem we have an unbiased estimator W and a sufficient statistic T. We proved that, or it was proved in Rowe-Blackwell theorem, that phi of t, which is a function of t equal to the expected value of w given t, does not involve theta. Therefore, it is a statistic. Also, it was proved in Rowe-Blackwell theorem that phi of t is an unbiased estimator for k of theta, and that variance of phi of t is less than or equal to variance of w. Therefore, phi of t is a better estimator compared to w, better of course here in the sense of having smaller variance. Now let us start the example. In the example we have a random sample x1, x2 till xn drawn from the Bernoulli mass function. As you know, the Bernoulli probability mass function is given by theta power x 1 minus theta 1 minus x. Here we have x takes values either 0 or 1, and theta lies between 0 and 1. We are given in the example that w equal x1 is an unbiased estimator of theta. Notice here that x1 is not the first order statistic or the minimum, it's just the first observation, it's not order. And also it is given in the example that t equals summation xi is a sufficient statistic for theta. We want to find an unbiased estimator for theta with no longer larger variance than w. It means we want to find an unbiased estimator for theta such that its variance is less than or equal to the variance of w, which is equal to x1. So again, according to Rowe-Blackwell theorem, we have that phi of t, which is the expected value of w given t, and we have that the variance of phi of t is less than or equal to the variance of w. So in order to illustrate the theorem, we have to show that in this particular example, variance of phi of t is less than or equal to variance of w. So now we have that phi of t, which is the expected value or the conditional expectation of w given t, and here because w is equal to x1, it will be the conditional expectation of x1 given t. This because here we have a discrete random variable, so this will be equal to the summation of x1 times the conditional probability that x1 equals small x1 given t equals small t. Notice here that x1 takes values either 0 and 1, so we are going to sum over the values of x which are either 0 and 1. So the conditional expectation will be given by the summation of x1 from 0 to 1, x1 conditional probability that x1 equals small x1 given t equals small t. So if we substitute for x1 by 0, we are going to get the first term will be 0 times the probability that x1 equals 0 given t, plus when we substitute by 1, we get 1 plus the probability that x1 equal 1 given t. Now notice that the first term will be 0. The only case where the first term can give an indeterminate quantity is if we multiply 0 by an infinite value. But of course here the probability can never be an infinite value, because the probability always lies between 0 and 1. So always the first term will be 0, so we are left only with the second term, 1 times the probability that x1 equal 1 given t, which will be equal to the probability that x1 equal 1 given t. This means that the conditional expectation of x1 given t will be equal to the probability that x1 equal 1 given t. So we want to calculate now the probability that x1 equal 1 given t. Now, in order to calculate the probability that x1 equal 1 given t, we recall that from the rules of probability, you took this rule in the course of probability 1, I think. We have that the conditional probability of A given B is equal to the probability of A intersection B over the probability of B. So here we are going to use this rule. We are going to assume that A is equal to the event x1 equal 1 and B is equal to the event t equal t. So the conditional probability that x1 equal 1 given summation xi equal t can be written as the probability of A intersection B. The probability of A given B. So the probability of A given B using this rule will be the probability of the intersection. In this case, we are going to consider probability of x1 equal 1 intersection summation xi equal t, and instead of the intersection we can use a comma. So here the comma in the numerator means the intersection, and this will be divided by the probability of summation xi equal t. So we want to calculate this function or these probabilities. Now notice something, that we cannot say that the event x1 equal 1 and the event summation xi equal t, that they are independent. No, they are dependent. Why? Because here in the first event we have x1 equal 1, and when we come to the summation xi, we know that summation xi from I equal 1 to n means x1 plus x2 plus x3 and so on till xn. So we have that x1 is common in both the first event and the second event. Since we have the same term in the first event and the second event, we cannot say that the two events are independent. So you remember there was a rule for the intersection in the case of independent events, which is probability of A intersection B is equal to probability of A times probability of B. We cannot use this rule for these events, but we can do some sort of manipulation which will enable us to use this rule. What are we going to do? We are going to say that for the second event, which is summation xi from I equal 1 to n equal t, we can write it as x1 plus summation xi from I equal 2 to n. So we are going to split summation xi from I equal 1 to n to two parts. One of them is the first term, which is x1, plus the rest, which is summation xi from I equal 2 to n. So again, the conditional probability will be written as the probability that x1 equal 1 intersection or the comma summation xi from I equal 2 to n plus x1 equal t. And in the denominator we will have the same probability that summation xi from I equal 1 to n equal t. So now if we note that here we are considering the probability that x1 equal 1. So if we replace x1 equal 1 in the probability in the numerator, then we can say that we have probability that x1 equal 1 intersection probability summation xi from I equal 2 to n plus 1. We are going to replace x1 by 1 plus 1 equal t. After that we are going to take this one to the other side. So we will have the second event in the numerator will be summation xi from I equal 2 to n equal t minus 1. Now if we notice we have the two events x1 equal 1 and summation xi from I equals 2 to n equal t minus 1, there will be two independent events. Because here in the second event we don't have x1. So we can use the rule of independent events, and we can replace the intersection by the multiplication. So the numerator will be the probability that x1 equal 1 times the probability of summation xi from I equal 2 to n equal t minus 1. Whereas in the denominator we have the same probability summation xi from I equal 1 to n equal t. Now I want to evaluate each probability. If we start by the probability x1 equal 1. Remember here we are using the Bernoulli distribution, and we have of course a random sample, so we have identical random variables. So we can go to the formula of the Bernoulli distribution, which is theta power x, 1 minus theta, 1 minus x, and just replace x by 1. We are going to replace x by 1 in the formula of the Bernoulli distribution. If we do that, we will find that we will have at the end theta. What will remain will be theta. So again, theta power x, 1 minus theta power 1 minus x. If we substitute for x by 1, the formula will be just theta. So you can see that in the numerator we have theta. Theta here is the probability that x1 equal 1. After that, we want to calculate the probability that summation xi from I equal 2 to n equal t minus 1. Notice here that when we sum xi from I equal 2 to n, we have n minus 1 observations. Because we have started with 2, not with 1. So we don't have n observations, we just have n minus 1 observations. This summation is equal to t minus 1. Now we can find the probability mass function of t minus 1. T minus 1 will be the same as n minus 1 independent observations, and they are identically distributed. Each one of them follows a Bernoulli distribution. So we have n minus 1 independent Bernoulli random variables, of course a Bernoulli with parameter theta. So the summation will be of course binomial, but here binomial has the parameters n minus 1 and theta. N minus 1 again because we have n minus 1 random variables, not n random variables. So we can say that t minus 1 follows a binomial distribution with parameters n minus 1 and theta, and that's what we did in the numerator. We have written the probability mass function of the binomial distribution, which is n minus 1, choose t minus 1, theta power t minus 1, 1 minus theta power n minus 1 minus t minus 1. This is the numerator. For the denominator, it's very easy, of course, because in the denominator we just have n random variables. Each of them follows Bernoulli distribution, and they are independent. So we can say that their summation from I equal 1 to n will follow binomial distribution with parameter n and theta. So in the denominator we are going to write down the probability mass function of the binomial distribution, which would be n choose t, theta power t, 1 minus theta power n minus t. Now we want to simplify the numerator and the denominator. First of all, we notice that the term theta and theta power t minus 1 will give me theta power t. So in the numerator, when we simplify theta and theta power t minus 1, we get theta power t. So theta power t in the numerator will cancel with theta power t in the denominator. Also, if we come to the term 1 minus theta, we notice that in the numerator we have 1 minus theta power n minus 1 minus t minus 1. This power will simplify to n minus t. Notice that 1 minus theta power n minus 1 minus t minus 1 will simplify to 1 minus theta power n minus t. So we have in the numerator 1 minus theta power n minus t, and in the denominator we also have 1 minus theta power n minus t, so they will cancel with each other. So all the terms which involve theta or 1 minus theta will cancel with each other in both the numerator and denominator. So we will be left with the term n minus 1 choose t minus 1 in the numerator, and in the denominator we will be left with the term n choose t. So we want to simplify these two terms together. We are going to use the factorial. As you know, n minus 1 choose t minus 1 is n minus 1 factorial divided by t minus 1 factorial times n minus t factorial. This for the numerator. Whereas for the denominator, the term n choose t will be n factorial divided by t factorial times n minus t factorial. So now we want to simplify these terms together. You are going to notice that the term n minus t factorial will cancel with the term n minus t factorial. So at the end we will have n minus 1 factorial over t minus 1 factorial divided by n factorial over t factorial. Now notice that t factorial, which is in the denominator of the denominator, will go to the numerator. So t factorial in the denominator of the denominator will be in the numerator. So we will have n minus 1 factorial t factorial, and this will be divided by t minus 1 factorial n factorial. This will be the final, or the terms will simplify to this. So now we want to simplify further. Notice that t factorial can be written as t times t minus 1 factorial. So we are going to write t factorial as t times t minus 1 factorial. Also in the denominator we are going to write n factorial as n times n minus 1 factorial. When we do that, we are going to notice that n minus 1 factorial in the numerator will cancel with n minus 1 factorial in the denominator. Also we are going to notice that t minus 1 factorial in the numerator will cancel with t minus 1 factorial in the denominator. So at the end we will be left with t over n. So the final answer, or the conditional probability at the end will be equal to t over n. Notice that the conditional probability is the same as the conditional expectation. So it means that phi of t, or the expected value of x1 given t, will be equal to t over n. T, of course, is summation xi from I equal 1 to n, and this will be divided by n. So this will give us x bar, or the sample mean. Now, so here this means that the estimator, which is 5t in this particular example, is x bar. Now, of course, we know that x bar is an unbiased estimator for theta, because in the Rowe-Blackwell theorem, this conditional expectation, which is 5t, should be an unbiased estimator for theta, and of course x bar is an unbiased estimator for theta. Now we want to get the variance of x bar and show that this variance is less than or equal to the variance of x1. Now, what is the variance of x1? Remember here that we have a random sample, so we have IIG observations. So the variance of x1 will be the same as the variance of x, or it will be equal to sigma squared. For the Bernoulli distribution, sigma squared is equal to theta times 1 minus theta. So for variance of x1, it is equal to theta times 1 minus theta. Whereas variance of x bar is equal to sigma squared over n, sigma squared, which is equal to theta times 1 minus theta divided by n. So variance of x bar is equal to theta times 1 minus theta over n. We want to compare these two terms together to see which one has a smaller variance. Now notice that for n greater than 1, variance of phi of t will be less than variance of x1. Notice that from the previous slide, variance of phi of t is equal to theta 1 minus theta over n. So obviously theta 1 minus theta over n is less than variance of x1, which is theta times 1 minus theta. But for the case n equal 1, we will have that variance of phi of t, or variance of x bar, will be equal to variance of x1. This means that variance of x bar is always less than or equal to variance of x1. So now we have illustrated Rowe-Blackwell theorem through this example. We have shown that if we have an unbiased estimator W, in this particular example it was x1, the first observation, and if we have a certain sufficient statistic t here, which was equal to summation xi from I equal 1 to n, we can show that first of all the conditional expectation of W given t, which we call it phi of t, is an unbiased estimator for our parameter. So in this case we showed that phi of t, which is x bar, of course it is an unbiased estimator for theta. Also we showed that variance of phi of t is always less than or equal to variance of x1, so we can say that phi of t is a better estimator than x1, better in the sense that it has smaller variance. So Rowe-Blackwell theorem helps me to get a minimum variance unbiased estimator, but as we said before, it does not say that this estimator is unique. Now we are going to move to another concept known as completeness. We are going just to understand this concept and illustrate it by some examples, but next lecture we are going to show how we can use this concept to get unique minimum variance unbiased estimators. So let us start now by defining completeness, the concept of completeness, or what do we mean by complete family of densities. The definition says that if we have a random sample x1, x2 till xn from a certain density, here the density we don't mean a probability density function. The density here we mean a distribution which can be either continuous or discrete. We denote it by f of x and theta, and it has a parameter theta which belongs to omega. Notice here that omega denotes the parameter space. Parameter space means the values of theta, the possible values of theta. And also let t be a statistic. The definition says that the family of densities of t is defined to be complete if and only if the expected value of u of t equals 0 for all theta belonging to omega, implies that u of t itself should be equal to 0 for all theta belonging to omega. Here u of t is a function in t, so it does not depend on theta, so we can consider it also as a statistic. If this definition is satisfied, we say that t is complete. Also, if t is complete, we can also say that the family of densities of t is complete. So let us try to understand this definition. What does this definition say? It says that if I have a certain function in t, we are going to call it u of t, then if expected value of u of t equals 0, implies that u of t itself has to be equal to 0 for all theta. In this case we say that u of t is a complete statistic. Or we can alternatively say that the family of densities of t is complete. Before taking examples to illustrate this concept, notice here that what do we mean by the family of densities of t is complete. Here we have, let us take an example. If we consider, for example, the normal distribution. The normal distribution, we have two parameters, mu and sigma squared. So if we consider a certain value for mu and a certain value for sigma squared, we have one member of the family of densities of the normal distribution. Now, if we change the values of mu and sigma squared, we get another member of the family of densities of the normal distribution. So the family of densities means all the members of the density which of course vary according to the values of the parameters. So it means the family, all the densities for all the different values of the parameters. When we change the values of the parameter, we get a different member of the family. So what we are saying here, when we say that a certain statistic is complete, this is satisfied for the family of densities, not just for one member. It means it is satisfied for all the members of the densities, because it is satisfied for all the values of the parameters. It is a definition which applies for all the values of the parameters, not only for certain values. So when we show that the expected value of u of t equals 0 implies that u of t itself has to be equal 0, this applies for all values of theta, not only for a particular value of theta. And also it has to be defined for all t, for all values of t. Now we are going to illustrate the concept of completeness through two examples. The first example is for a discrete random variable, and the second example will be for a continuous random variable. For the first example, we have a random sample from the Bernoulli distribution, and of course you are now very familiar with the probability mass function of the Bernoulli distribution, which is theta power x 1 minus theta power 1 minus x. X takes only two values, 0 and 1, and theta takes values from 0 to 1. And we want to show that t equals summation xi is a complete statistic, or alternatively, we want to show that the family of densities of t is complete. Now, to show that t is a complete statistic, we have the function u of t. Let u of t be any statistic that is a function of t for which the expected value of u of t equals 0 for all theta. Now, if we want to show that t is complete statistic, we must show that u of t is equal to 0 for all theta, and of course for all t. Now, if we want to evaluate the expected value of u of t, notice here that t equals summation xi, and because we have Bernoulli random variables, they are independent and identical, we know of course that their summation will be binomial with parameters n and theta. So in order to get the expected value of u of t, we are going to sum u of t with respect to the probability mass function of the binomial distribution. And of course here t takes values from 0 till n. You know that the summation xi will take values from 0 to n. So we can say that the expected value of u of t will be equal to summation from t equals 0 to n u of t, and choose t theta power t 1 minus theta power n minus t. So first of all, we can simplify a bit by noticing that 1 minus theta power n minus t can be written as 1 minus theta power n multiplied by 1 minus theta power negative t. So again, we are going to write 1 minus theta power n minus t we are going to write it in the form 1 minus theta power n times 1 minus theta power negative t. And then we are going to take 1 minus theta power n outside the summation, because it does not depend on t. So we are left with 1 minus theta power negative t. We are going to take theta power t times 1 minus theta power negative t. This will give me theta over 1 minus theta all raised to the power t. So again, theta power t times 1 minus theta power negative t will give me theta over 1 minus theta all raised to the power t. So what do we have now? The expected value of u of t will be given by 1 minus theta power n multiplied by summation of u of t and choose t theta over 1 minus theta power t, and we are taking t from 0 to n. We want to show that if the expected value of u of t equals 0 for all theta, this implies that u of t itself should be equal to 0 for all theta, and of course also for all t. Here expected value of u of t equals 0 implies that summation u of t and choose t theta over 1 minus theta power t from t equals 0 to n should be equal to 0. Notice here that 1 minus theta power n is not equal to 0 because here, as we said, we want the expected value of u of t to be equal to 0 for all theta, not for a particular value of theta. So again, we want the summation of u of t and should t theta over 1 minus theta power t to be equal to 0. We are going to call theta over 1 minus theta alpha. So the expression will be summation u of t and should t alpha power t from t equals 0 to n equals 0. We want this to be equal to 0, the summation to be equal to 0. When will this summation be equal to 0? Notice that we have here a polynomial in alpha. Polynomial in alpha means we have a term, for example, alpha power 0 plus another term, alpha power 1, and so on. So we have a polynomial in alpha. So in order that this polynomial, for it to be equal to 0 for all alpha and for all t, each coefficient of alpha power t should be equal to 0. We must have that u of t and should t equal to 0 for all t and for every term of alpha power t. Now what does it, so again, I will repeat again, and now we have a polynomial in alpha. Why? Because we have terms of alpha to the power t. So it is as if we have, for example, if we substitute by 0, it is as if we have u0 and u0 and alpha power 0, which is 1, plus u1 and u1 alpha power 1, plus u2 and u2 alpha power 2. It's like a polynomial in alpha. In order that this polynomial equals 0 for all alpha and for all t, it has to be that the coefficients must be equal to 0. So we must have that u of t and choose t equals 0 for all values of t. Notice now that n choose t can never be equal to 0. So this means that it has to be that u of t equals 0 for all t. Like this, we have proved that t is a complete statistic, or that the family of densities of t is complete. Because remember, to show that t is complete, we had to show that the expected value of u of t equals 0 implies that u of t itself is equal to 0. And that's what we got here. We got that it has to be that u of t equals 0. And this is satisfied for all t and, of course, for all theta. That means that t is complete, or the family of densities of t is complete. Now we are going to illustrate the concept of completeness, but in this example we are going to consider a continuous random variable. We are going to assume that we have x1, x2 till xn random sample taken from a uniform distribution defined over the interval 0 and theta. Notice here that this means that the probability density function of the uniform distribution will be 1 over theta. 1 over theta, and x takes values from 0 to theta. We want to show that the statistic xn, which is the nth order statistic, is complete for theta. So now we want to evaluate the expected value of u of xn. Notice here that xn is a continuous random variable, so we need to know its probability density function in order to be able to evaluate this expectation. Now remember that we can get the probability density function of the nth order statistic using the formula f of xn equal n capital F of x evaluated at xn. Of course, capital F is the cumulative distribution function, power n minus 1 multiplied by the probability density function of x evaluated at xn. Now we notice that for the case of the uniform distribution, we have that the cumulative distribution function of x will be x over theta. So if we substitute x by xn, we get xn over theta. So we are going to get n xn over theta raised to the power n minus 1 multiplied by 1 over theta. Of course, 1 over theta is the probability density function of x, and the probability density function of x is the same as the probability density function of xn because it does not depend on x. So now we are going to evaluate the expected value of uxn, which will be the integration from 0 to theta, xn multiplied by the probability density function of xn, and of course here we are integrating with respect to xn. Now I'm going to get the terms which do not depend on xn outside the integration. So we will have n over theta power n, and then we are going to integrate from 0 to theta u of xn power n minus 1. This will be the integration we want to evaluate. Notice here that n over theta power n is not equal to 0. So what do we want to show? We want to show that the integration from 0 to theta xn power n minus 1 gxn equals 0 implies that uxn itself has to be equal to 0 for all xn. We want to show that if this integration is equal to 0, if the integration from 0 to theta xn power n minus 1 dxn is equal to 0, this implies that uxn itself should be equal to 0 for all xn. Notice that the integration in the previous slide is difficult to evaluate. So what are we going to do? We are going to use a certain formula or a certain rule which will enable us to give a simple expression for the integration. This formula or this rule is the rule of differentiating and integration. So let us read the rule first and then see how we can apply it for our particular example. What does the rule say? It says that if we want to differentiate with respect to theta a certain integral, the lower limit of this integral is g1 of theta, which is a function in theta, and the upper limit is g2 of theta, which is also a function in theta, and we are going to integrate the function f. F is depends on both x and theta, and we are going to integrate with respect to x. It says that the differentiation of this integration is equal to differentiating first the upper limit, so we are going to differentiate g2 of theta with respect to theta multiplied by f, and in f we are going to substitute for x the upper limit of the integration. So instead of x we are going to put g2 of theta. So the first term again is the derivative of the upper limit of the integral, which is g2 of theta. We differentiate g2 of theta with respect to theta and multiply this by f, but instead of x we substitute for g2 of theta, minus the second term is what? We are going to differentiate the lower limit with respect to theta, so it will be partial g1 theta partial theta, and then in the function we are going to substitute x by the lower limit, which is g1 theta. So the second term will read partial g1 theta with respect to theta f g1 theta. This is the second term. What about the third term? The third term means that we integrate from g1 theta to g2 theta, and inside the integral we are going to differentiate the function f of x theta with respect to theta, and of course here the integral is with respect to x. So this third term will be the integral from g1 theta g2 theta, the derivative of the function f of x theta with respect to theta. This is the rule of finding the of differentiating the integral. We are going to apply this rule in our integration. So notice that our integral is the integral from 0 to theta xn power n minus 1. We are integrating with respect to xn. So first of all, we are going to differentiate the upper limit with respect to theta. So the upper limit is theta. So as if we are getting the derivative of theta with respect to theta, partial theta with respect to theta. After that, we are going to substitute in the function with the upper limit. Our function here is xn power n minus 1. So instead of each xn, we are going to substitute by theta, the upper limit. So it will be u of theta power n minus 1. So the first term will be the derivative of theta with respect to theta, and when we substitute in the function, instead of xn by theta, we get u of theta, theta power n minus 1. Now for the second term, the second term should be what? The derivative of the lower limit with respect to theta. Notice that the lower limit here is 0. So when we differentiate 0 with respect to theta, of course we get 0. So all the second term will be 0. Now if we move to the third term is what? It is the integral, and then we should differentiate the function with respect to theta. Our function here is u xn power n minus 1. Notice that our function here does not depend on theta. So if we differentiate it with respect to theta, we get 0. So also the third term will be 0. So here for our particular integral only, we get a value for the first term, whereas the second term will be 0. Again, why it will be 0? Because we are differentiating in the second term 0 with respect to theta, and of course this will be 0. And also the third term will be 0. Why? Because in the third term we have the integration of the derivative of the function with respect to theta. Our function is u xn minus n minus 1. It does not depend on theta. So if we differentiate it with respect to theta, we get 0. So we only have for our particular integral partial theta with respect to theta, u of theta, theta power n minus 1. We equate this to 0, and at the end we want to show that this implies, if we have xn is a complete statistic, this implies that u xn should be equal to 0 for all xn. That is what we want to show. Now notice that if we differentiate theta with respect to theta, of course we get 1. Also this means that we will have the term mu of theta, theta power n minus 1 equals 0. Now notice also that theta power n minus 1 is not equal to 0, because as we said, we want the expression to be satisfied for all values of theta, not for a particular value. So theta power n minus 1 will not be equal to 0 for all values of theta. So we must have that u of theta itself equals 0. U of theta should be equal to 0 for all theta. If we replace theta by xn, this means that u of xn should be equal to 0 for all xn. And this is exactly what we wanted to prove. We wanted to prove that if the expected value of u of xn equals 0, this implies that u xn itself should be equal to 0 for all xn. So since we proved that, we can say that the family of densities of xn is complete, or xn itself is a complete statistic. So now we have illustrated the concept of completeness. In the next lecture, we are going to see how we can make use of this concept and also of Rowe-Blackwell theorem to get a unique minimum variance unbiased estimate.